Hello everyone, my name is Savehshemshaki. Today I'm going to talk to you about our paper entitled A Robust Receding Horizon Collision Avoidance Strategy for Constrained Unmanned Ground Vehicles Moving in a Shared Planar Environments. My supervisor, Dr. Walter Lucia, and I have done this work at Concordia University. The outline of this presentation is as follows. First, I'll explain the scenario behind this work, then we'll see how the problem is formulated. After that, the way our novel strategy is proposed, and finally, we'll see some simulation examples and future works. The scenario of this work is that we are considering a set of S heterogeneous UVs moving in a shared planar environment, and each UV is equipped with its reference generator that provides its reference trajectory. Between vehicles' trajectories, there are possibilities of collisions. There is no intercommunication between vehicles, but vehicles share information with a common centralized unit named Traffic Manager or TM. There are physical limitations, pose constraints on vehicles' states and inputs. The UV's model that we are considering here is described by the constraint discrete double integrator model as follows, where X is the state space vector in which P shows the vehicle's position and V shows the vehicle velocity, and the system is subject to a bounded disturbance D and the following state and input constraints. All these sets are compact sets, including 0. To have a better perspective of our problem, we must consider some assumptions. The reference generator provides the reference trajectory as a sequence of NP waypoints, and the maximum distance between two consecutive waypoints is bounded by delta. We also assume that a limited vision radius as a finite sequence of waypoints, namely waypoint prediction horizon, is available. The control problem that we are facing here is that regardless of disturbance realization and input and state constraints, UVs are required to, as a first objective, sequentially track the given waypoints under different velocity constraints, and as a second objective, avoid collision with a minimum number of stop occurrences while following the reference. We have proposed a novel control architecture that consists of a set of S local tracking controllers based on the dual mode set theoretic model predictive controller or MPC to satisfy the previously mentioned objective 1, and a centralized traffic manager that predicts collisions within the prediction horizon and imposes time-varying velocity constraints or stop conditions to the vehicle to ensure an absence of collision and minimize the number of stops. This traffic manager fulfills the objective 2. To address the first objective, the set theoretic MPC tracking controller operations are used here. To see how the single waypoint tracking is done, let's take a look at the offline and online operations. Offline, we need to build an RCI region and design the associated stabilizing controller for this RCI region. And also, we need to build a family of N robust one-step controllable sets until the desired state space region is covered. Once we have the families of one-step controllable sets computed offline in the online phase, first we need to find the minimum set index membership that the initial condition, or let's say the current states, belongs to. Once we have the position of the current state, we have one controller to move the state to the terminal region and another controller to keep the states within the terminal region. Now we need to know how the waypoint switching and tracking a sequence of waypoints is done by using the set theoretic MPC. For the considered UV model, an equilibrium pair is as this one. Moreover, no state constraint on the vehicle positions are prescribed. Then the family of one-step controllable sets centered in the equilibrium state can be shifted to any other equilibrium, which is in our case the next waypoint, and then the set theoretic MPC can be applied as explained in the previous slide. As it is proved in our TAC paper, this is there is a necessary condition for a feasible waypoint switch, and this condition is that the next family of one-step controllable sets around the next waypoint must contain the previous family's RCI region. The whole waypoint tracking controllers used in this paper is summarized in this algorithm, which I explained in detail in two previous slides. There are two important remarks about tracking the waypoints. The first one is, whenever necessary, the vehicle can be safely stopped in the terminal region associated with the current waypoint by disabling the waypoint switch step, which is this step 2 here. The second remark is that the controller above enjoys recursive feasibility for time invariant constraints X and U. Now we need to see how the set theoretic MPC is feasible under TM operations. Let's revise the TM desired operations, which are predicting collision and defining max velocity for each vehicle, or stopping vehicles whenever strictly necessary. For these aims, we need to make the following assumption. A finite set of L admissible velocity constraints are imposed for each vehicle, which is this V satisfying this condition. Therefore, the state constraint XLI is used to denote time-varying state constraint. So the set theoretic MPC must be revised to ensure recursive feasibility. Now to see how the set theoretic MPC works with the time-varying velocity constraints, we need to revise the offline and online operation. Therefore, in the offline phase, the RCI region must be built using the worst-case velocity constraint scenario, which is minimum velocity constraint. And then, for each velocity constraint, a family of one-step controllable sets must be computed and built from the same RCI region. In the online phase, the constraints switch, which means the state constraints of velocity level 1 switches to the state constraints of velocity level 2 are enabled. And this happens when the current state enters the domain of attraction of the controller using these state constraints, which is for velocity level 2. And there are two important remarks about this procedure. First, when the constraints is relaxed, switched from 1 to 2, the condition above is instantaneously verified. Second, the worst case scenario, the switch happens when the common RCI region is reached. Before designing the traffic manager, we need to know the data exchange between the traffic manager and UVs. Offline, each UV sends the family of one-step controllable sets computed for each velocity level and the associated controller domain to the traffic manager. And online, each UV sends the predicted waypoints and the current set membership index to the traffic manager. Based on the data exchange and collision avoidance objective, TM operations are twofold. First, it should impose the vehicle's velocity constraints to minimize the possibility of a collision between the vehicles. And second, it should ensure the absence of collision by stopping whenever strictly necessary the minimal subset of. We can model the TM as a function like this one, in which we are getting the waypoint prediction horizon, this R, and each vehicle set index membership as an input of this function. And then TM provides this for each vehicle that can be either stop or go. And if the status is go, TM assigns the velocity levels, this Li, and to each of the vehicles that the status is go. As mentioned in remark 5 here, given the set theoretic MPC operations, TM can safely stop a vehicle only in the terminal region of the current waypoint. So, to determine the outputs, 3 steps must be taken by the traffic manager. In the first step, TM must build and update the collision graph. At t equals 0 or offline phase, TM computes an undirected collision graph. Let's take a look at this figure in which we are showing an example of 8 vehicles. We are showing the vehicles by nodes and the possibilities of collisions by edges. The collision graph characterizes the vehicles based on their collision in the waypoint prediction horizon, which we are showing with the red nodes and solid purple lines, and the vehicles that have the possibility of collision with a current waypoint, which we are showing now with the green nodes and dashed purple line. At t greater than 0 or online, in a receding horizon fashion, only portion of this graph must be updated. In the second step, TM needs to decide which vehicle it needs to stop. As it is stated in remark 6, only vehicles that just updated the desired waypoint can be stopped. In other words, vehicles which are in the terminal region of their current waypoint can be stopped. With this information, let's take a look at this figure in which we have a portion of the previous graph. In this graph, vehicles 2, 3, and 8 are in their terminal region of their current waypoint, and they want to switch to the next waypoint, while vehicle 5 is far away from its current waypoint and it hasn't reached it yet, so we cannot stop vehicle 5. Among these 3 vehicles that want to switch to the next waypoints and have possibility of collisions in their current waypoints, TM must stop the minimum number of vehicles in order to get this whole graph completely disconnected. So it stops vehicle number 3. In the third and last step, TM wants to minimize future collision. So it considers all the vehicles that were not stopped in the previous step and groups them, as you can see here, based on their possibilities of collision. And it tries to speed up and slow down the vehicles of each group to avoid reaching the collision point at the same time. To do so, in each group, it finds the distances to the next possible collision point. And as mentioned in remark 7 here, the exact future trajectory is unknown, and this equation approximates the distance as the summation of the second norm distance between the waypoints. Therefore, for each group, it collects the computed distances in an ordered vector. And proportional to those distances, it assigns the velocity levels to each vehicle. These velocity levels are assigned according to heuristic solution. This heuristic solution aims to differentiate the velocity level as much as possible. And as mentioned in this remark 8, to allow the closest vehicle to overcome the collision point before the other vehicle could reach the same collision area, we use this heuristic solution. To illustrate the effectiveness of our proposed solution, we simulate an example. The general setup for this example, as you can see here. 2 vehicles are considered and described by double integrator models, subject to different input constraints and disturbances. And a family of n robust controllable sets computed for each velocity levels has been computed for each vehicle. And also 3 admissible velocity levels are considered. In this figure here, we are showing the trajectories that each UV is tracking. And here, the number of stops imposed by traffic manager has been evaluated for different waypoint prediction horizons between 1 to 300. In this figure, we run the simulation for different prediction horizons because when the prediction horizons gets bigger, it means that the traffic manager has information about more future collisions. So it can prevent collisions before the vehicles reach the collision points, and we expect the stop occurrences to decrease. Therefore, as you can see in this figure, as the waypoint prediction horizon increases, stop occurrences decrease. For the two previously mentioned vehicles, let's consider prediction horizon of 15. If we refer to the middle of the figure in this zoom in, at t equals to 85.5 seconds, this shows the situation when both vehicles are in the terminal region of their current waypoint and they want to switch to the following waypoints. But because there is a possibility of collisions, as you can see here, there is a set intersection which we show with this orange area. Therefore, TM stops vehicle 1 and let vehicle 2 pass. Let's take a look at these figures in which we are showing the different velocity levels and the stop commands assigned to each vehicle. For example, for UV2, when the waypoint prediction horizon is equal to 1, TM stops vehicles for 10 times. But when the prediction horizon has increased to 250, vehicle 2 has never been stopped. On the other hand, for UV1, when the prediction horizon is equal to 1, the period of stop is greater than when the prediction horizon is 250. In conclusion of this work, we can say this work extends the collision avoidance strategy developed in our tag paper. In particular, compared to that paper, the presented solution is capable of exploiting a prediction horizon on the waypoints to minimize the number of vehicles stopped required to avoid collisions. And as a future work, we can extend the proposed solution to work with more complete, like nonlinear model of UVs, such as differential drive robots or car-like vehicles. We can also enhance the traffic manager operations, taking into account more sophisticated collision risk, such as the time to collisions and priorities among vehicles. Thank you so much for your attention to this presentation.